Hi, I'm John DeNero. I teach computer science and data science here at Berkeley, and I helped develop this course called Data 8, The Foundations of Data Science, which started nearly 5 years ago and has become one of the very most popular courses on campus and has influenced similar courses in many colleges and universities around the world. I suspect many people watching this video know a little bit about the course already, so my goal here isn't to describe it, but instead to reflect on some of the design decisions that we made. So thanks for watching for a few minutes, and if you want to follow up with me, I'd be delighted to hear from you. There's my email, so feel free to let me know if you have comments or suggestions or questions. Is data science interdisciplinary? Data science involves a combination of computing, statistics, and domain expertise about whatever domain is under study. But I think describing data science as interdisciplinary actually doesn't quite get it right, because it assumes that the disciplines that I've just described are the right way of carving up the intellectual landscape. That computer science is one set of ideas, and statistics has another, and economics another, and mathematics another, and public health another, and that data science would somehow draw from all of these in order to be interdisciplinary, that it would live somehow on the boundary between these. But I think that way of carving up the intellectual landscape was a very reasonable first pass in an era before computing became so essential to understanding the world around us. Without having a computer as a primary inferential tool, all of these different disciplines had to come up with their own mathematical techniques that were constrained not only by what problems a particular domain was interested in, but also what inferences could be carried out using closed-form solutions and probability distributions that were well understood. But I think our growing understanding of computing technology has changed that story somewhat. I think that we often consider computers as changing the world because of the applications that are developed. But computers have also changed the way in which people draw conclusions from data. They've changed the way in which we can understand and make predictions about the world around us based on incomplete observations. And there we reach the core of data science, which is really about creating useful descriptions and drawing robust conclusions and eventually making reliable predictions about the world, even in cases where the world is so complicated that it can't be described using a page full of equations. And we do this using the data we have available, along with an understanding of where that data came from, how it was collected, and what it means, and properly accounting for the uncertainty that still persists in the understanding of our world, because our data are always incomplete descriptions of the complex world that we want to study. And so I would say that this act of analyzing or understanding the world based on observations is not interdisciplinary, but instead is core to so many different disciplines. And while once it made sense to use different techniques in different domains because we were constrained by what could be achieved using closed-form mathematical solutions, now the same visualization and simulation techniques are applicable in lots of different areas. And yeah, they involve computers in order to make those descriptions and inferences. And I think part of the goal of Data 8, which brings together students from lots of different corners of campus at Berkeley, is to promote the idea that there is this common skill of being able to describe the world based on incomplete information or observations and draw useful conclusions anyway. That pervades many different disciplines, and that's what data science is all about. So Data 8 is a first course, mostly first-year students take it, that introduces people to the process of analyzing data. It also introduces the students to programming so that they can carry out the computational techniques with full generality. They're not constrained by particular settings in which a technique would apply, but instead can program their computers to do whatever they need them to do. So a quick description of the course is that we teach students to program Then we teach students about statistics, using programming as a tool, and then we introduce machine learning with some of the ethical implications of these along the way, and using real-world examples in order to illustrate everything that's taught in the course. But that quick description leaves out some important details. We don't teach people everything about programming. We don't teach them everything about statistics, and certainly not everything about machine learning, but instead have selected particular topics within these general disciplines that we think fit together nicely, are fundamental to lots of different domains, and help students think about data-driven problem solving and analysis in a useful way that they can build on in future courses when they learn about more mathematical techniques, more programming techniques, and become experts in their domain of interest. So here's a chart of the majors, or at least the intended majors, of students when I taught the course back in spring 2017. I know this is dated, but I bring this up because it's before we launched the data science major here on campus. So now if you looked at this pie chart, you'd see a big wedge of data science majors who are taking it because it's part of the program. What's interesting is that when I taught this course back in spring 2017, it wasn't required for any of these different majors. Students were taking it out of interest because they understood the value of working with data in the great variety of different disciplines that they were interested in. And, the larger wedges of this pie chart correspond to some of the larger majors on campus. But what's wonderful is that so many different majors are represented in the population. This was true back in spring 2017. It's true now, and the course has grown a great deal. Back then, there were 680 responses to this question. Now we see enrollments of close to 1,500 students in some semesters. Okay, so I said that there's a programming element, there's a statistics element. Let me talk a little bit about what students learn about computational thinking in computing. There are lots of different topics that exist in a typical computer science introductory course that also exist in Data 8, although the form is often different in that we're more selective in Data 8 about teaching students just the computational thinking ideas that they need in order to work with data. So for example, a typical introductory computer science or CS1 topic is that students should be able to read and write compound expressions that involve variables and multiple data types. And in Data 8, this is certainly a focus. But instead of talking about a vast array of types, including trees and linked lists and hash tables, we really just focus on two and understanding them deeply. Those two are tables. There's a custom representation of a table that we use in the course, that we developed for the course. And also arrays of numbers or arrays of strings, where students learn in particular about the NumPy implementation of an array. They do need to understand what's going on in code, and they get a lot of practice, for example, distinguishing between names that are assigned values in the environment of the interpreter and strings, which are values themselves. So instead of writing long programs in Data 8, students are mostly focused on writing compound expressions that do something interesting. So here is an expression that sums the salaries of all players in the NBA, these are basketball players, whose heights are above 80 inches. And they need to be able to construct expressions like this one, where they're summing values in the salary column of a table, where first we've selected for rows where the heights of the players are above 80 inches. And they have to distinguish between the fact that sum and NBA are names for functions and tables respectively, whereas height is a data value that's passed in to a method in order to indicate a particular column that's being filtered. We actually avoid a lot of language syntax and semantics in the course. We don't talk about mutating values. We don't talk about operator overloading. We don't talk about a lot of things that could be discussed in an introductory programming course, in order just to focus on this core idea that compound expressions are built from simpler expressions in order to describe computations that are then carried out by the interpreter in order to get you what you want from the things that you already have. So this expression is built off of a custom implementation of a table that we use in the course that has a where method and a column method, and also has this built-in syntax for coming up with predicates that can be used for filtering. And this implementation of tables is quite a bit simpler than industry standard tools like pandas because it uses a limited syntax of the Python language. So you just don't have to learn as much about how programming works in order to be productive. So the pandas equivalent of this would be that you want to sum the salary column of the NBA table, where you filtered that NBA table based on its height. A seasoned programmer would really have no problem understanding how this table works, which is a pandas data frame. But there are a lot of things about this expression that can be problematic for students just learning to program. What kinds of values go inside square brackets? Well, here we have a string. Here we have some other large expression. And what is this large expression? Well, it's actually generating an array of Boolean values, which is then put in square brackets. And because the pandas item selection operator is quite flexible in terms of the data types that can be used within it. And explaining to a student why they need to refer to the NBA table twice, once in order to get the salary column, and again in order to get the height column, is just a tricky thing to convey. So when we use square brackets in Data 8, they always have just numbers in them. So we teach them about element selection from an array, but avoid this fancier stuff. And we never talk about Boolean arrays as the way in which you filter a table, but instead just talk about predicates, which are functions, and students understand functions pretty well by the end of the course. Okay, anyway, so students learn about compound expressions, but they don't learn about all the different types of compound expressions that exist in the Python programming language. We just focus on the ones that are most important, which are nested function calls and method lookups. Another typical introductory computer science topic is to learn how to generalize processes by defining functions. But we do not focus in Data 8 on how to decompose a large program into smaller modular parts using functions. And we do not focus on abstraction. Instead, we focus on the simple act of first analyzing a specific example, then writing a function that could analyze similar examples. So they might write that the variable state is bound to the string CA, and then they get the population of the state of California using an expression that refers to the state variable. But what about other states? Well, they could rerun this code, assigning state to something else, or they could write a function which selects the rows of the population table for a particular state, and that state is the input to the function that they've defined. That's kind of the limit of the function definition work that they do in Data 8. It's an important first step in understanding the role of functions to generalize processes, but there's more to learn if they take computer science courses later. They learn about iteration. A typical topic in an introductory computer science course would be to design and implement iterative procedures. In Data 8, we just focus on the most obvious examples, where the interpretation of what's going on is quite interesting, so the conclusions you reach are cool, but the code is not cool in itself. The most common application of iteration is to perform multiple simulations of some random process. So for example, we might take samples of a table and collect the sample means so that we can visualize those. That output visualization is interesting, but the iteration itself, do something 1,000 times, is typically not. So in this sense, Data 8 is not a programming course or an introductory computer science course, in that it doesn't try to push students to combine these ideas in new ways, but it does build a foundation for understanding the role of syntax and programming languages in writing down computational simulations, which is what they need in order to do interesting data analysis later in the course. But Data 8 is more than about computational thinking, it's also about inferential thinking. How do you draw conclusions from incomplete observations that are robust and take into account whatever uncertainty you have? we teach students an approach to analyzing data that is not particular to this course, but instead would show up in any introductory statistics course. The idea that with data, an analysis starts with a question from some domain that you'd like to answer requires making some reasonable assumptions about the data and choice of methods, and then you perform the visualization and calculations that allow you to draw those conclusions, and finally, an interpretation of the results in the language of the domain without statistical jargon. So we focus a lot on what it means to run a hypothesis test or compute a confidence interval, as opposed to just how to compute them. However, where Data 8 departs from other introductory statistics courses is that we perform very few calculations, but instead use computation and particular simulations of random processes in order to draw whatever conclusions need to be drawn. In this way, we avoid what some students really dislike about introductory statistics courses, which is to be presented with formula after formula and the many simplifying assumptions that are behind each formula, and then just having to trust that they apply correctly. With computational simulations, students are actually able to try stuff out. They can inspect the results and decide whether those results seem reasonable to them, which helps build intuitions about correct statistical inference. There's a motto of the course, which is visualize, then quantify. We push students to try to understand a holistic picture of the data and the question they're trying to analyze before they go compute the p-value of a hypothesis test. And we structure the whole course this way. So while they're learning the fundamentals of programming, they're just focused on description and visualization. So by the end of this section, they're able to work with tables, filtering, grouping, joining. They can define functions, compute various descriptive statistics, and create a large array of visualizations, where we focus mostly on histograms, but they build all kinds of things. So one example is that we use bike sharing data, and it turns out that you can learn a lot about the geography of the city of San Francisco just by looking at how long it takes to bike from one place to the next. After students learn to describe the differences between data sets, they naturally ask, are those differences real? Everybody's familiar with this folk notion of statistical significance, even if they don't know quite what it means. And one major goal of this course is to make that understanding clear and precise. So we move from description and visualization into chance, into models, into hypothesis testing, and other forms of inference, in particular focusing on the notion of a confidence interval and how to compute a confidence interval using bootstrap resampling. And from there, we move into correlation, prediction, and machine learning techniques. The machine learning part of this course doesn't focus on algorithms. In fact, the only prediction algorithms that we cover in the course are simple linear regression and k-nearest neighbor classification. But we do try to help students understand the notion that training data is a sample from a distribution, and that the goal of prediction is typically to make inferences about examples that have not yet been observed, and the host of issues that arise in that setting. And we try to teach all of this with real data. Arrays, tables, visualizations, inference, regression, and classification can all be introduced with real-world data sets. If we really push ourselves as instructors, we can avoid inventing data sets for almost everything we want to teach, at least in a course like this. We didn't start this way. Early on, there was a lecture on roulette, because that was a natural way to introduce probability, but it's been removed. There was a lecture on randomized surveys as a way of maintaining privacy, but that was removed. And what was added in their place? Well, there's now a lecture on comparing students who attended tutoring sessions with those who don't, and trying to understand whether there's a difference in outcomes. It's a great problem because it turns out the students who elect to attend tutoring have quite a different distribution in test performance than those who don't go to tutoring. If you just look at their absolute performance, then it's lower. But if you look at the amount that they improve from an exam taken before tutoring and one after, then you can see that they improve more than comparable students who didn't attend tutoring. And this kind of analysis, I think, can show up in lots of different places. But by giving students a real example with real data that's relevant to them, we've found that they're more willing to engage in the subtle issues, like how do you account for the fact that students weren't assigned to attend tutoring or not attend tutoring randomly, but instead had a choice in the matter. We added a lecture on the health impact of replacing butter with margarine, which involved a great deal of careful experimental design and also some subtleties in analyzing the results. For probability and for teaching about join operations on tables, we still start with artificial examples. There's still discussions of colored tickets and restaurants with made-up prices, but almost everything in the course starts with real data, even in the simplest examples. Okay, I'll wrap up by just saying a little bit about course materials. There's a free online textbook, inferentialthinking.com, and it's an executable textbook, meaning that for every section of the textbook, there's an associated notebook that was used to generate all the figures and code examples in the textbook, and with one click, you can start interacting with that as a Jupyter notebook so that you can tweak the examples yourself as a student and understand what's going on. This is licensed under the Creative Commons, meaning that it can be republished if you want, as long as it's not for commercial purposes and gives proper attribution, and also has a no derivatives license, which means that you can't take the textbook and rewrite parts of it and republish it that way. Instead, we think of it as a coherent whole. You're welcome in your course to assign only parts of it and to post anything you want as supplemental material. And in fact, all the infrastructure for creating the book and other executable books is here as free open source software. But there is just one version of the book, and we try to take some care to make sure that it's an intellectually coherent whole, and that's why we have a no derivatives license. There's also quite a bit of software associated with the course. There's a data science module, which includes that implementation of tables, makes it easy to work with maps, simplifies the syntax required in order to do common table operations, like filtering and grouping and joining, and gives access to a standard set of visualizations in a simplified syntax, so that students can create bar charts and histograms without knowing too much about the matplotlib module that is, while wonderfully powerful, at least a little bit complicated to master. Students work in Jupyter notebooks, so they don't have to work with source files, they don't have to install everything, and I would say that Jupyter Hub, which allows us to host all of their notebooks for them, is now robust and easy to administer. In 2015, there were some technical hurdles, but nowadays it's not so bad at all. This hosted computing environment gives stable configuration, so you know that all students are working with the same version of every module. And we do have some tools for authoring notebook-based assignments and grading those notebooks that you're welcome to use. For small to medium-sized courses, there's an Otter grader framework, which lets you take a bunch of notebook submissions and grade them all. And for developing new notebook-based assignments, there's something called JAssign, where you write one notebook that's got the assignment and the solution and the tests all in line, and then JAssign breaks it up in order to hide the solutions, hide some of the tests, and store the rest of the tests away so that they're accessible to students, but not a distraction for them. And this approach gives students a way to incrementally test their work as they go, which I think is important as a learning tool, makes them more self-sufficient as well. And then they can submit their assignments using a framework called OKPy, which some instructors like. We use it a lot at Berkeley. It was developed here, and we use it for computer science courses and also for data science. Okay, thanks for listening. I hope that gives you some idea of why Data 8 is the way that it is. In terms of the actual course content, I'll trust that you can look through it yourself. All of it is publicly available at data8.org.